Yes.
Okay, sweet. Thank you guys. Um, yep, we have a couple of people here. I think we can get started then. Okay. All right. Okay, cool. So, hey everyone, welcome to the first session of program two. Today we will be doing algebra, and in particular, we will be talking about sequences. Okay. Oh, also, wait, I should just turn my camera on. You guys are all welcome to like turn your camera on as well, um, so that we can see like if you have any questions, if you want to raise your hand, or yeah, like show how you're feeling. That can be really helpful. If not, that's fine, but we do recommend that. Um, yeah, otherwise, some basic rules would just be like make sure that you put up a hand, be respectful in the Zoom chat, and yes. Okay, so hopefully this whiteboard works. Right. Oh yeah, and also I should probably introduce myself. So my name is Nicole. I graduated from Kristen School last year, and in September I will be going to Stanford. Maybe studying math, maybe studying electrical engineering or something. So yeah, nice to meet you guys. And also in Maths Olympiad, I was in the Indigenous squad for 2023 and 2024. Cool. Okay, so today we will be talking about what sequences are, then secondly, going over some basic kinds of sequences, thirdly, talking about a technique we call telescoping, and for kind of applying everything we learned to the Fibonacci sequence. And after that, if we have some time, we'll be going over some little snack problems. Okay, so the first question would be, what exactly are sequences? Actually, does anyone want to give it a try in the chat and tell me what sequences are? Patterns. Yeah, very good. Good job. Okay. Yeah. So sequences are pretty much like patterns indeed. Like you have like a chain, yeah, like a pattern, right? So you have like a chain of numbers, kind of, and then like you can find some kind of relationship between them a lot of the time. I mean, sometimes like there isn't even a pattern when you have a sequence. Like it literally is just like a sequence of numbers, like a list of numbers almost. But I think the important thing to know with sequences is that numbers are like placed in a certain order, right? Okay, so yeah, so they have a certain order and they often do follow a certain rule or a pattern. So one of our most common sequences that you see all the time would be the sequence of natural numbers, right? So 0, 1, 2, 3, 4, all of the integers, positive, the non-zero positive, sorry, the non-negative integers are in the natural numbers, right? And then we also have like the sequence of odd numbers, so 1, 3, 5, and 7, and the sequence of even numbers, 2, 4, 6, 8. And then in the last one, we have the sequence of powers of 2, starting from 2. So then we get 2, 4, 8, 16, and so on, right? So at each step, we're increasing like the term and it's going to follow like a certain rule. So when we're talking about each term in the sequence, then we refer to it as the nth number in the sequence, right? So say, for example, in the sequence of the odd numbers, right? Then our nth number in the sequence, say we had our third number in the sequence, then that would be 5. Okay, can I zoom in a little more? How does this work? Wait, let's zoom out. Okay, cool. Yeah, so for example, here, since we're taking the third number in the sequence, then we would get 5. If we were to take like the, oh, this is moving around a lot. Okay, yeah, and then if we were going to take the fourth number in the last sequence, then we would get like 16, right? Okay, so hopefully that makes sense, but let me know if anyone has any questions, then you can just say in the chat if you'd like. Okay, so let's go through a couple of examples together. So firstly, what would the nth term be of the sequence of positive integers? Is anyone able to give me like a general form? So if we had like a bunch of positive integers and we wanted to count n of them, then what is the number that we would end up on? Ooh, really, really close, you guys. Yeah, n is correct. Good job, good job. Yeah, yeah. So let's just quickly write that out. And yeah. I mean, infinity also like, yeah, maybe I worded that a bit weirdly, but it's just as like we have like n, which we kind of like assume is finite here. If we had n going to infinity, then yeah, that would be the nth term. So yeah, that does make sense. Okay, but I mean like in this sense, we're gonna assume that n is like, I guess, a finite number. So if n was like 5 or something, then we would only count the fifth term. So yeah, exactly, right? So n, great job, great job. Yeah, so maybe I said that a bit weirdly. How do I draw? Where's the drawing thing? Eh, what? Shape, line, text. Hold on, I just need to find my pen. Hmm. Okay, give me a second, guys. Oh, how am I spelling this person? Where is the pen? Okay, I'll just do text for now. How do I do text? Okay, there we go. So we're counting our positive integers, right? And then this would be like A1. Oh, let's not do that notation for now. But just note that the first term would be 1, the second term would be 2, third term would be 3, fourth term would be 4, and all the way on, right? So we know that the nth term for this one is just going to be n. Term is n. I think categorically we don't take 0 to be a positive integer. I think it counts as non-negative integer, but generally when we refer to the positive integers, then we don't include 0. But that's a good question because this is really applicable when we're talking about the natural numbers then, right? So natural numbers, can anyone tell me what the nth term would be in this case? Yeah, really good. That would be n minus 1, right? And the reason why we have that is because now we're starting from 0. So we're kind of like one step behind almost, right? So our first term would be 0, our second term would be 1, third term would be 2, and so on. Nth term, term is n minus 1. Okay, nice. And what about the sequence of negative numbers? Yeah, a lot of good attempts in the chat, guys. Keep it up. Okay, so our answer can just be achieved by writing it out again, right? So our first negative number, I guess, would be -1 because 0 isn't included, right? So we have -1, -2, -3, and so on. So then our first term is -1, second term is -2, third term is -3, and so on. So then our nth term is going to be -n. Cool. Okay. And then what is the pattern of the following sequence? 1, 3, 5, 7, 9, and so on. Anyone want to give this a go? So we want to find like a general expression for the sequence, right? So it's like if we were talking about the nth term, we would want to be able to like put it into some kind of formula that then gives us our number in the sequence. So in the previous examples, we've kind of expressed the sequence using a general form, which is that if you know the value of n, you can directly plug it in to say -n or n-1 or n, and then we will get an output which corresponds to our number in the sequence. So what we're looking for here is just like a general form. So given that you're looking for the nth term, you only need to know n and then the general form so that you can then plug it in and then get what you want. So I think someone has got the answer here. Yep, awesome. So let's just have a look at how this works. I still haven't found my pen, which is very interesting. Okay. Anyways, I'll figure it out later. Okay, so here we have our pattern 1, 3, 5, 7, 9. So what this looks like is just going to be like the sequence of odd numbers, right? And we can see here that the difference between each number is going to be 2. So that means that as n increases by 1, the nth term increases by 2, right? Because as we're increasing n in increments of 1, so we're going from the first term to the second term, or the second term to the third term, then the term in the sequence is actually increasing by 2 each time. So we know we have a 2n in there because as n increases by 1, the whole output is going to increase by 2. We note, right, that we actually start at 1 as well. So if we're looking at the first term and we input it into 2n, then that would give us 2, right? So we have to adjust this a little bit to ensure that our first term gives us a 1. So that means that the nth term is 2n minus 1. So good job to the person who got that. Yeah, nice. Okay, hopefully that makes sense, right? So if you were to plug in n equals to 1, then you would get 2n minus 1 equals to 1. And if n equals to 2, then you would get 2n minus 1 equals to 3, and so on. Cool. Okay, and then one last one like this. What is the pattern of the following sequence? 1, 2, 4, 8, 16, 32. Yeah. Mm. Mm-hmm. Yep. Really nice. Okay, so we can see here that the sequence is what we call geometric, right? Between each term, you have a common ratio. So instead of like adding the same thing between consecutive terms, you're multiplying between consecutive terms. So you can see from 1 to 2 and 2 to 4 and 4 to 8, all of that, you're just multiplying it by a factor of 2, right? So we know that you're going to get something with 2 to the power of something with respect to n. So it turns out that is going to be 2 to the power of n minus 1, right? Because n minus 1, exactly, great job. Because we know that our first term equals to 1, right? So we have to ensure that 2 to the power of n minus 1 equals to, we have to ensure that 2 to the power of something is going to equal to 1, right? Which means that if 2 to the power of something equals to 1, then we need something equal to 0, right? So that means that for n equals to 1, then we actually require this something to equal to n minus 1. Cool. Nice. Really great job, guys. You guys are doing real well. Okay, let's have a look at our next slide then. How do I change slide? Okay, great. Oh, maybe I should get rid of all of this. Okay, cool. Okay. I still can't find my pen. Let me search it up. Click the pencil icon. What? Why can't I see the pen? Hmm, that's super weird. Does anyone know where the pen is? Like, because I think you guys can draw on the whiteboard as well, right? So, can anyone see a pen? My one? Just on the left-hand side. Yeah, I have like the select, then the eraser, then shape, line, text, sticky note, and whatever. But I can't see the pen. Just so weird. Okay. Oh, wait, do I need to convert it from an eraser to pen? Oh my gosh, thanks, guys. Oh wow, that's so smart. Okay. Yeah, I was like, that is so weird. There's no way. But that makes a lot of sense. Okay, thanks so much. Okay. Anyways, okay, so before we were talking about how we can define the nth term using like a general form, right? So we also want to kind of tighten up our notation a little bit. So something we often use is a, and then we kind of write like n in the subscript, which denotes the nth sequence, the nth term of a sequence, right? So we often use an, but we might also get like bn or cn or like anything n, right? And it doesn't always have to be n as well. It could be like k, it could be j, but this notation is often what we use to denote like the nth term or the kth term of like a given sequence, right? Okay, so something that we also see a lot of time is like when we're kind of indexing in a sequence is that we also have like a m plus 1. So this is used to describe the m plus 1th term in a sequence as opposed to just like the a n to as opposed to the nth term in the sequence. So when we write this out, we're often just trying to establish a relationship between the n plus 1th term with the terms for it, right? And this is not the only thing that we see. We also see a 2n, or like a 2n minus 1. And this is a really, really good way of separating the even terms, well, the even terms in your sequence and like the odd terms in your sequence. So sometimes that can also be pretty helpful if you're trying to like identify a pattern that alternates. So a lot of the time when you get a problem about sequences, you'll be trying to find a general expression for a given n, and or you'll be trying to find like a certain n that fulfills a condition so that the nth term equals to something. Okay, cool. Okay, yeah, so there are two ways that we often define sequences. The first way being recursively, and the second way being through a general formula. So before we went through some like general formulas, right? So we said that for our sequence of positive integers, that an equals to n. And we said that for, what is it? The natural numbers equals to n minus 1, and so on, right? But there's also a lot of ways that you can define. So this is the general formula, right? But when we're defining things recursively, then we kind of have another way of like displaying what our sequence is relative to the previous term. So if we were to look at the sequence of positive integers, like this, 1, 2, 3, 4, and so on, we can see that each one is just going to be the previous one increased by 1, right? So now what we can actually do is say that am plus 1 is just going to be the previous term, an, and then all of that plus 1, right? So now we can define it in a way that we call recursive, because its relationship is based on how it is like related to like the previous term, right? So given that an plus 1 equals to an plus 1 for the positive integers, oh, another important thing is that we also need to set like the initial condition, right? Because in a relationship like this, you don't know what your starting point is. So if you were to do a recursive definition for the sequence of positive integers, then you would also want to set a1 equals to 1, right? Because from this, we know that the difference between consecutive terms is 1, but we don't necessarily know from where the sequence starts. So these are our two important specifics. So now this is for the positive integers, right? Can anyone tell me how we would recursively define the sequence of natural numbers? Yep, great. Okay, yeah, amazing, right? So we know our sequence of natural numbers is going to start from 0. So we're going to go 0, 1, 2, 3, and so on. So we know that the difference between terms is still going to be 1, right? So this recursive relationship, an plus 1 equals to an plus 1, still works. The only thing that we have to change is our starting point, right? So when we define the sequence, we would just set a1 equals to 0, and then everything else is still going to work. Okay, cool. Let's try, yeah, let's try doing one more recursively. So let's say we have How about the powers of 2? The powers of 2 starting from 2 to the power of 0. How can we define this recursively? Okay, so remember, yeah, it is true that we have a general form of 2 to the power of n minus 1, right? This is kind of what we got before. But, I mean, more so, this time we are looking for the relationship between our terms, right? So how can we relate an plus 1 to an? Yeah, really good, really good. Okay. Yeah. So we're wondering how we can relate this somehow to like just an, the term before it. And then now we come to the conclusion that our way of doing that can just be by multiplying the previous term by 2. So an plus 1 equals to 2an. And then we set, yeah, you double each term, exactly. And you want to set the first term equal to 1, right? So instead of giving a general formula in which you can just plug in n, right? Because in this general one, if we know n, we know what the output will be. In this case, in the recursive definition, what we do is we do it relative to the term before or like other terms before. So that's why we're able to just multiply the previous term by 2 and then get to our new term, right? So we're defining an plus 1 based on an. So this is how we could define it recursively. And of course, we want to set our initial condition as well. Okay, hopefully that makes sense. But yeah, you guys are doing super well. Keep it up. Okay. Yeah, I think we already kind of covered this, so let me get with that. Okay, so now we're going to talk about some basic kinds of. Oh, another example? Yeah, of course. Yeah, we can do that. Um, let's do one more. Let's do the sequence of odd numbers. Yeah, sequence of odd numbers. So we want to find the recursive definition. Yeah, how about we can actually just walk through this one together. So when we're looking for the sequence of odd numbers, we have that the general form, right? Hold on. The general form of the nth term is going to be 2n minus 1, right? Because before that, we have already established, based on the sequence, I think, in an earlier slide, that the first term, since it equals to 1, then we need to have 2n minus 1 here. Because we know that the difference between each of the terms is 2, right? That means that as n increases by 1, then the whole output is going to increase by 2. So that's why we have the 2n, right? So that's accounting for like our common difference. But we also need to consider the starting term, right? Which in this case is 1. So we want to have that 2n minus, sorry, not minus, 2n like, yeah, plus k, or some k equals to 1 when n equals to 1. So then that means that 2 plus k equals to 1, and then k equals to -1. Wait, I am not still working on the first slide. Wait, what? Okay. Oh, what? I'm on the 9th slide. Wait, can you guys just are you guys able to like switch between the slides yourself? Oh, what?
I can only see the first slide.
Oh, okay. Thanks for letting me know. Wait, that's quite that is not good. Maybe if I extract a really long um wait. Okay, extract all pages. Okay, now we have all 45. Can everyone see this? Mm, okay. Okay, yeah, I'm not sure why it doesn't just like change slides when I click change slide. Maybe the whiteboard's a little weird. Okay, so right now we are on. Okay, how do I? Okay, I'm gonna go into basic sequences right now. Maybe if you guys like follow me, like, because I think you can kind of track where I'm at. So maybe that will work. But right now I'll just be on the basic sequences side. Okay, and then we're going to move to the arithmetic sequences side. And hopefully you guys are seeing this. Okay, cool. So like we were talking about before with the sequence of odd numbers, right? We talked about how there's going to be a common difference, which we can kind of define using k or like d, c, any other constant. And then, right, we found what the relationship between an plus 1 and an is. So we found that to be an plus 1. Oh, wait, we're still finding it, right? Okay, yeah, so we look at the difference between each of the terms and we just add 2, right? And we also define the first term to be 1. So as opposed to the general form, we have an plus 1 equals to 2n minus 1. We're instead looking at this recursive definition where by knowing the previous term in the sequence, then you can find the next one, okay? After that, let's move to, yeah, let's talk about one important property of arithmetic sequences, which is predictiveness, right? So this is how we're able to find a general. So given that we know the general expression for the nth term in a sequence, then we're able to predict the value of the nth term for all n, right? Which is really, really useful. So suppose we have the nth odd number as, what is it, 11,111. Can we find n? Does anyone want to let me know if they have any idea as to what it is? Yeah, you can just plug it in, right? Yeah, okay, so let's give that a try then. So yeah, good job, Luna. That's really good. Okay. So this number equals to 2n minus 1, right? So then 1, 1, 1, 1, 2 equals to 2n. And then therefore, n equals to 5,556. So now we know that 11,111 is the 5,556 number. odd number, right? Yeah, it's approximately half, right? Because we are like alternating between odd and even, so it's close to half. Yeah. Okay. Yes, so we got that right. Okay, now let's talk about the sum of the first n terms in an arithmetic sequence. Find the sum of the first n terms of the sequence. Do we know how we could come up with a formula for the sum? Okay, yes, we can go through this one together actually. So let's kind of start by experimenting a little, right? Let's say that we have two terms in our sequence. Then sum of the first two terms, which we can denote like this. Yeah, great job, great job. Okay, yeah, someone has got it. Let's just go through it real quick though. So this would give us A1 plus A2, right? And we know that A2 can be written like recursively. So we know that A2 actually equals to A1 plus K, right? So what that actually gives us is 2A1 plus K. And then if we were to do this with S3, then we would get like 3, 3A1 plus 3K. And then S4 would be equal to 4A1 plus 6K. And then S5 equals to 5A1 plus 10K, I'm pretty sure. Okay, so now we kind of see some pattern going on because, well, when we add up the terms and then define them recursively, then we can see that you can write all of the sums in terms of just A1 and also the common difference K. So there we have that. So now it looks like our formula is kind of going to be of this form, right? It looks like you're going to be adding up A1 n times because that's included in like every component of the sum, and then K is included n minus 1 times for every term in this, for the n minus 1 times for the nth term in the sequence, right? Because, say for example, A3 is going to be like A2 plus K, which equals to A1 plus K plus K, right? So this is going to be 2K. So for the nth term, then you kind of get the common difference n minus 1 times. Okay, so how can we simplify this now? Um, hmm. Okay, yeah. So now we know that we can simplify this by kind of factoring out n. So this is what we can get. Right, because we know that the sum of all the numbers 1 plus 2 plus all of that and so on until n minus 1 is going to be equal to n times n minus 1 divided by 2, right? So because we want to multiply that by k, we just add that in. Okay, so now we have this general form for the sum of an arithmetic sequence. And then this is going to be pretty helpful for a lot of our computations. And also there's a pretty intuitive way of thinking about it as well. So let's just say we use a pretty simple sequence of numbers. Let's just say we go from 1, 2, 3, all the way up to 8 and 9. Okay, and then in between here we have like, I'll just write it out. Okay, so we have our integers from 1 to 9. And then we're wondering, how can we really quickly find the sum of the sequence, right? Because sometimes when sequences get long, they can be pretty tedious to add up one by one. So a really good way of doing this is by kind of pairing the terms up, right? So if we pair up 1 and 9, then these sum to 10. 2 and 8 also sum to 10. 3 and 7 also sum to 10. 4 also sums, 4 and 6 also sum to 10. And then 5 is like half of 10, right? So what that means essentially is if we're adding like the terms on opposite ends, so like the first term and the last term, or any other pair, then you'll be getting 1 plus 9, which is 10, right? And then we're left to ask, how many pairs are there? Well, there's 1 and 9, that's 1, 2 and 8, that's 2, 3 and 7, that's 3, 4 and 6, that's 4, and then 5 is half a pair, so then that's like 4.5 pairs, right? Which is the number of terms divided by 2. So we're just going to multiply that by 9 divided by 2. So essentially what we've done here is we're looking at the number of terms n divided by 2 to give the number of pairs, and then we're multiplying this by the sum of each pair, which would be like m plus 1 in this case, right? Okay, so hopefully that makes sense, but let me know if anyone has any questions. Yeah, let's just do this exercise. So 3 stages of a pattern are shown above and below using matchsticks. How many matchsticks are required to make the figure in stage 100, and which stage would require 250 matchsticks? Does anyone want to give it a go? Actually, I think we'll just go through it since we don't have like too much time. But look, at every stage, we're adding like another box, right? And to add another box-like shape, we're adding 3 matchsticks. So we could express our general form an equals to 3n plus something. Since we know that each time you're adding 3, that means that as n increases by 1, then the whole output has to increase by 3, right? So that's why we use 3n. And then we want to add some constant k to better define our sequence. So we know at stage 1, when n equals to 1, then the total number is going to equal to 4, right? So 4 equals to 3 plus k, and thus k equals to 1. Yeah, really good, guys. That's so good. Good job in the chat. Okay, so then if we were to plug in n equals to 100, so we get a100, that's going to equal to 301. Really good. And then now we can do it the other way around to find which stage would require 250 matchsticks. So we know that 250 equals to 3n plus 1. And because of that, we're able to solve to get n equals to 83. So at the 83rd stage, you would require 250 matchsticks. Nice. Okay, good job. So in terms of geometric sequences now, we kind of talked about this before as well, but what you do when you define it recursively is you're multiplying things by a common ratio, right? So suppose we had this, then an plus 1 equals to 2 times the previous term, right? And then when we're talking about constructing a general formula, sorry, we know that we're going to be multiplying by 2 a lot of times. And then what we found before is that an equals to 2 to the power of n minus 1, right? So in this case, the common ratio that's changing between each of these terms is 2. And that's what we often call r. So we say like r equals to 2 or something like that. Okay. So we are now kind of able to call our general term as like r equals to n minus 1 times a1 for whatever we set a1 as, right? Because before we said like for the powers of 2, we have 2 to the power of n minus 1. And then sometimes you also want to like multiply that by something depending on what our initial value is. So before, when we had our initial value as 1, then we can just make a1 equal to 1, and then that's all good. Okay, so let's talk about how we can sum these up, right? Because we talked about how we can find the sum for an arithmetic sequence, and now we want to think about how we can do that for a geometric sum as well. So if we are to sum up each of these terms, then we get a1 plus r plus, sorry, plus a1 r squared plus a1 times r to the power of n minus 1. So this is supposing that we have our n terms in sequence, right? So let's think of a way that we can really nicely make a general form, because this is quite ugly to add up, right? You have to compute every single term and then add it up manually, and that takes a really long time. So the first step that we can do is factor out the a1, which is what we've done here. And then after that, let's think about this. I feel like if you've seen this factorization before, then you might kind of get it. If not, I'll just kind of tell you this really cool factorization, which is that 1 plus r squared all the way up to r to the power of n minus 1, all of that times r minus 1 actually equals to r to the power of n minus 1. Now that's really clean, right? So what we can do is rearrange this to say that r to the power of n minus 1 divided by r minus 1 equals to 1 plus r plus all of those terms plus r to the power of n minus 1. So now we have this really nice way of expressing it. This is much cleaner because if you're trying to find out the sum, all you have to compute now is just r to the power of n minus 1 and then r minus 1, right? Instead of like adding up in terms. So yeah, this is a lot simpler. And what this is going to give us is that our sum formula will just be all of that. So r to the power of n minus 1 divided by r minus 1, and all of that just multiplied by our first term, a1. So now we have a really, really nice formula for how we can do geometric sums. Okay, so yeah, quick exercise. Let's do, prove that the sum of the first n terms of 1, 2, 4, 8, 16, 32 is 2 to the power of n minus 1. So how can we approach this? Well, we know that this is a geometric sequence with the common ratio r equals to 2, right? And we also know that the first term of our sequence equals to 1. So all we have to do is actually just plug this into our formula. So we know that we have r to the power of n minus 1 divided by r minus 1 times a1. So then what does that give us? That just gives us 2 to the power of n minus 1 divided by 1, because that's just 2 minus 1, and then times 1, which is a1. So then that's just going to give us 2 to the power of n minus 1. Nice. So yeah, this formula is super applicable, because imagine having to sum up like so many powers of 2, right? This is so much faster. So yeah, I think it works quite well. Let me know if you have any questions about this. Otherwise, I'll just wait. I don't need to write this out. Do I? Oh, I should. Okay. And then now let's just quickly actually move to this concept that we call sum convergence, right? Okay, because when we're adding up a geometric sequence, then you kind of always have this small space, right? Like you're adding up bits and bits, and you're often summing it up so that it's getting closer and closer to like filling a space, but it's never quite there, but it is getting closer and closer. And that's when we talk about the topic of convergence, right? So when you have a geometric sum, and then you're getting this extremely large n that's like going to infinity, then we're thinking about what happens when you're trying to add all of the things up. So when the ratio of a geometric sequence of a series is strictly less than 1, so when r, the absolute value of r is strictly less than 1, then for larger n terms, right, since you're taking r to the power of n minus 1, then each term an is going to be getting closer and closer to 0, right, because you're multiplying it by something that is less than 1. So you're going to be left with something that is going to be getting smaller and smaller and smaller. And therefore, actually does converge. So when you add up the sum of such a sequence, then you're going to get closer and closer to this like finite value, right? So what do we actually get when there is an infinite number of terms? So we know that we have, for the general formula for the sum of a geometric sequence as r to the power of n minus 1 divided by r minus 1, and all of that multiplied by a1. So we know that this is for like a finite kind of n, right? But what happens as n goes to infinity? Well, we can, I guess, take the limit. So as n goes to infinity, then we still have a1, but r to the power of n is going to be going to 0, right? Because it's going to be getting smaller and smaller because you're multiplying it by a number that's less than 1 many, many times. And then, oh, yeah. And then here you still have r minus 1 on the bottom. Okay, so does it kind of make sense why r to the power of n goes to 0 as n goes to infinity? Hopefully, let me know if you have any questions about that. And then all we have to do now is just kind of expand this. And this gives us negative a1 divided by 1 minus r. Wait, no, sorry, my bad. Not 1 minus r minus 1. And then I usually just like to write this like a1 divided by 1 minus r. Okay, so when you actually have an infinite number of terms, then you get this formula for the sum. And this is really, really useful for a lot of questions. Let's take a look at one right now, which is that suppose that the common ratio is 1/2 for some geometric series. So in other words, the common ratio, like defined by this, is going to be applied to our n plus 1th term, like this. So we want to show that the sum of the first n terms as n approaches infinity is going to be approaching 2 times a1. So all we have to do is plug that into our formula now. We know that we just take a1 divided by 1 minus r. And in this case, r equals to 1/2, right? So now we get a1 divided by 1/2, which is just going to give us 2a1. So that's really cool. So this formula is actually pretty useful for a lot of sequences because it's quite common, I'd say. But yeah, let me know if you have any questions on how this works. I don't think we will get through all of this today, but yeah, let's just talk about telescoping really quickly. So telescoping is really interesting because sometimes when you have a certain sequence, then it's really, really hard to find the sum because it looks like you're needing to add up so many terms, right? But the thing here to note is that sometimes the terms can cancel. So suppose an equals to bn minus bn plus 1, and you want to find the sum a1 plus a2 all the way to an, right? Then all you actually have to do is expand. So a1 equals to b1 minus b2, right? And then a2 equals to b2 minus b3. And then you realize that a lot of the terms in the middle will literally just cancel out. So the minus b2 and the b2 here, they will cancel. And like the minus b3 and the b3 that's coming after that will cancel. And all of these terms will just cancel out until you're left with the first term and then the last term. So that can be really, really helpful for solving a lot of things. So let's give that a try with this one. So we are asked for the sum of all of the terms of this kind of form. Wait, let me not use that. So we're asked for the sum of terms with the form 1 divided by k times k minus 1, right? And then one really good way we can do this is by kind of splitting it into partial fractions, so 2 different fractions, and then trying to make them cancel, right? Because how can you really add up terms that are like 1 over 2 plus 1 over 6 and then like 1 over k times k minus 1 for so many terms? There's no easy way to do it apart from like if you do telescoping, really. So let's see how we can do that. So we want to set 2 fractions, a over k, and then b over k minus 1. So if we want to set this as equal to our left-hand side, then we want to kind of like rearrange this. So then we get a over a times k minus 1 plus bk over k times k minus 1, right? So these are equivalent. And then by expanding, we know that ak plus bk equals to 0 because here there are no k terms. And then we know that negative a equals to 1, because here you have a negative a, and then on the left-hand side you have 1. So now we know that a equals to negative 1. And because of ak plus bk equals to 0, we know that a equals to negative b. So then b equals to 1. So now when we split this into partial fractions, we actually get negative 1 over k plus 1 over k minus 1. So this is actually what we get when we're talking about a way of splitting it up into partial fractions. So when we're looking for the sum now, we'll be taking something like this for different half, and then wait, hold on. Yeah, so this is starting when k equals to 2, I believe, for the first term. Yeah, so then what we actually do is we can just kind of iterate through for each value of k, but instead of using this form, we're going to be using this form. And then that will help us kind of find some terms that can cancel out. So when k equals to 2, we have 1/2, right? And 1/2 can also be expressed in a different way. So that can also be equivalent to this, right? And then now we're talking about 1/6, which is when k equals 3. Then that's going to be negative 1/3 plus 1/2. And then we can keep on doing that. So and so on. And then we get negative 1/k plus 1 divided by k minus 1. So note that this is what we get when we set k equals to 2, k equals to 3, and k equals to 4. And then we want to keep on doing that with all of the values of k, essentially. So because we're able to split up each of these fractions into 2 different fractions, we can see that a lot of these components are actually going to cancel out. So you get the negative 1/2 canceling out with this one, the negative 1/3 canceling out with this one, and the negative 1/4 will also cancel with a term later on. So then what we end up getting is the terms that don't cancel, which would just be 1, and then 1/k. So now we have successfully telescoped, and then we know to find the sum, we only have to do 1 minus 1/k at the very end of the day. So yeah, hopefully that kind of makes sense. Telescoping, I think, is a pretty big step up, but because we also have to do the partial fractions, but hopefully that makes sense. Yeah. And then, yeah, that's probably going to be all for today then. So yeah, thank you so much for coming today. And also, if anyone wants to like ask me any questions, then feel free to just contact me at my email address. I'll just type into the chat. Feel free to contact me and ask any questions if you'd like. Yeah, otherwise, thanks so much for coming. Bye. But also good job with all of the problems. You guys did really well.